Yeah. So first of all, sorry for not able to make it this week due to various reasons from teaching to other things. So this week we already have two lectures on atmospheres of exoplanets and also brown dwarfs. So brown dwarfs are largely covered by Sujan, and then Jayesh has touched upon atmospheres from the perspective of radiative transfer. So, as all of you have seen from all the talks, atmosphere plays a big role for understanding the planetary formations and evolutions globally. And one of the key cornerstones for understanding planetary formation and evolution is to understand what chemistry is operating at scales, which is basically starting from the beginning to the end for during the evolutionary sequence. So today, what I'm going to do is I'm going to take you through the journey of foundational knowledge that one need to understand how chemistry operates from scales, so essentially from atmospheres back to the origins. And I have three aspects to that. So I will first introduce you. I will first introduce you to the broader perspective why we should care about chemistry and why chemistry is important and fundamental if you really want to decode exoplanets. Then I will take you through the journey of how chemistry can be modeled, where chemistry that we know in the atmospheres are in equilibrium. And if planet atmosphere deviates from equilibrium, if disequilibrium processes starts operating in the atmosphere, what type of chemistry plays a role in the atmospheres. Then if I get time, I will also give you some glimpses of the idea when these planets were formed, whether the chemistry that we see today in the atmospheres, both in terms of equilibrium and disequilibrium, how different they are when they were formed in these Caronian stars. And I will largely, take you to all the basics and some of the implications that we had. And then after this break, Priyanka will take you through the hands-on session for chemistry, how you can model chemistry using open source codes, because some of the results that we will be showing, they are not open source. So he will take you through the hands-on session using some of the open source codes such as Vulkan and FastChem, how we can understand equilibrium chemistry and disequilibrium chemistry in planetary atmospheres. So this is the introductions before I begin. So let's start. So I think all of you have seen this diversity of planetary populations already. So I don't need to explain in detail. But currently, as we know, we have already observed more than 6,000 exoplanets, and this diversity of exoplanets is seen both in terms of the mass and radius. But when you have access to the mass and radius, you get the idea about the planet bulk, planet bulk properties, but hardly you have any idea about the atmospheres. And atmosphere plays a large role in shaping the diversity of what we measure today in terms of the compositions. So starting from hot Jupiters to rocky terrestrial planets. So when you see this diversity for the hot Jupiters, majority of the planets are very close to their host star. So you can certainly think about the chemistry that operates at those scales, largely driven by the high temperature chemistry, along with incoming stellar photons. But when you are looking at the terrestrial atmospheres, which are largely in the outer part of your outer part of your planetary system. So the chemistry that will operate there will be much different than what you see in the hot Jupiter. So the chemistry in the terrestrial planets will be dictated by cold chemistry. So this largely because we see the diversity of the planets and chemistry follows this diversity. So the chemistry can be used as a tool to understand how these planets are evolving with respect to time, and also why and what might have happened in the past for these planets, so that they have started with the current bulk compositions, and which is essentially helping these planets to evolve over time. So and and we already have this diversity thanks to many facilities which have helped us to understand this. And you all know already TESS and Kepler has played a big role in decoding this diversity of exoplanets. And now with JWST, we are in an era where we can do precision atmospheric characterizations across different types of planet atmospheres. And as soon as we, start characterizing this, atmospheres, we see chemical diversity. So by chemical diversity, I mean some of the molecules that you see in one classes of planets, they are missing in other classes, or some of the molecules are, abundant across same types of planets. So this essentially tells you these chemical pieces are strongly sensitive to the environment where we are probing them, and they are tracing fundamental chemistry. And we need to understand how this fundamental chemistry, operates from at different temperature regions, different spatial locations, and how they're interacting continuously with your physical processes in this type of planets. So today, the current frontier for exoplanet science is essentially, we already have heard a lot of talk on formation and evolutions. And we also today heard about habitability from Ravi and Sourav. So essentially, by studying planets today, we get the understanding about how these planets were formed and also how they are currently operating. And do we see any signatures in the atmosphere that can potentially tell us how we whether these planets are habitable, and is there any possibility of detecting these signatures from the atmospheres? So if we start to understand this chemistry, then we really need to know how chemistry starts. So the chemistry starts even before the planets were born. Okay, so because we all know the planets were born from disks around young stars, and these disks are the processes from long, star and planetary evolutions. So it essentially started from molecular clouds, which are the large extended system of gas and dust, which eventually collapses to form protostars. And then eventually with time, you have disks. But the chemistry that operates from clouds to disk are much complex. And the molecules that we have detected so far during the evolution for star and planets are more than 300 molecules has been discovered in the early stages of planet formations. But if you see the atmospheres, we hardly have probably not more than 10 molecules which are securely detected in the atmospheres. So that tells you the molecules and the chemical ingredients that were available in the early stages during the formation of the planets are missing in the planetary atmosphere today. So what are the physical processes that cause that missing of large chemical inventory that we see in the early stages of the planet formations? And also, the composition that we see today in the atmospheres are also the process that happen in the early stages. So essentially, we can ask the question, how do the composition of the disk get incorporated into forming planets? And this is something that Bart had already covered in detail, and he showed how you can use the evolutionary models from early stages to get the understanding about how they are setting up the future atmosphere for planets. So we have all seen that. And the parameters that essentially controls the measurement of diverse chemical ingredient for planetary atmospheres is essentially linked with the ice lines for different molecules in protoplanetary disk. So here on the left side, you have already seen this figure from Bart's presentation, but still I would like to show to set the stage. What I'm showing here on the left side, I'm showing the carbon to oxygen ratio, and the x-axis I'm showing the radial dependence on carbon to oxygen ratio. So what you can see here in the outer part, so essentially it's a radial snapshot. In the outer part of the disk, where temperature is much lower, what you see here, you are measuring very high carbon to oxygen ratio in the gas phase. And as you go inside, your carbon to oxygen ratio in the gas phase is decreasing. And you can see the clear decrease in the carbon to oxygen ratio at different locations of the ice lines. Okay. So from outer part to inner part, the C by ratio is decreasing. Okay. So if you start thinking about on a very zeroth order scale, like if there is no migrations and my planets are forming through core accretion mechanism, then you can think about if you're, because these systems are largely made up with the gas and dust goes into the core of the planet. And when core grows, eventually the gas that is out there here is accreted by the planets. In that way, the bulk carbon to oxygen ratio in the disk stage, reflects what will be the expected initial carbon to oxygen ratio that will be available to future planets. And as a result of this carbon to oxygen ratio becomes one of the foundational tool for us to get the idea about how atmospheric diversity for planetary atmosphere could be used to understand its origin. But of course, there are several degeneracy problem arises from here because, of course, if you think about, as Bart has mentioned, if you think about the migrations, how the migration will change the location of these snow lines, then essentially you will also see change in the sea-bio ratio. So it's a complex problem, but at the same time, just measuring elemental bulk composition for the measured reservoir, which is your carbon and oxygen, you can really get first-order estimates about whether the planets has formed in the interior of your snow lines of major reservoir of carbon and oxygens, or they are formed outside of your major reservoir. So that gives you the idea about the pristine environment where these planets are accreting the gas from the disk around young stars. And that's one of the key driver that drives the field of planetary atmosphere, where we can use chemistry and chemical composition as a tool to understand the atmospheric origins of different classes of planet atmosphere and link them to the potentially back to their origins. So that's basically the origins part. But of course, the atmosphere itself is very exciting. And for many of the planets that I have shown in terms of the diversity, we know their accurate mass and radius. And you all know through several lectures in terms of radial velocity and transit, we can, as soon as you know the mass and radius, we get the idea about the density of the planet, and that gives you the idea about bulk compositions, but hardly that will give you any idea about the atmosphere. So we need atmospheric spectrum from planets to get the idea about the compositions. And when you have access to the atmospheric spectrum, and atmospheric compositions, that potentially tells you the atmospheric chemistry that is happening. And when you know this atmospheric chemistry, that gives you the idea about how these planets have formed and whether the atmospheric chemistry can be one of the false positive, which is potentially linked to the detection of biosignatures. So that's why atmospheric chemistry becomes foundational knowledge, not only to understand the formations of planets, but also at the same time to understand what we are detecting and how chemistry is playing a role in securing the detection of the molecules. And neither we are over claiming any detections related to life, or so basically we are considering it as one of the potential driver of forming this molecule. So every time we detect any molecules, we need to know whether is there any potential atmospheric chemical pathways exist which can lead to this molecule in this temperature environments, in this planetary environments, before making any comments regarding their potential role as habitability. So atmospheric chemistry thus plays a big role in also selecting what are your potential traces for future detection of in biosignatures for any planet that you are interested in. And you all have seen that. I don't need to explain you again, but this is potentially done with everybody's favorite technique, transmission spectroscopy, where your planet passes in front of your host star and you see deep in the starlight. And if you measure the starlight at different wavelength, then essentially you get the idea of what types of atoms and molecules present in the atmosphere. Higher is the light blocked, you get the higher transmittance, and essentially that gives you the idea about the concentration of amount of species that is present in the atmosphere. So now, if I really want to summarize, why we should really care about chemistry for atmospheres, chemistry essentially gives you the idea about, gives you the clues regarding formation and evolution for planets. which is one of the key frontiers for the field. Then when you know chemistry, if you measure atmospheric composition today from the planets, that gives you the idea about what is happening today in the planet atmospheres. So essentially, what are the dynamical processes that is controlling the atmospheric processes, which leads to the diversity of the atmospheric composition that we are measuring. At the same time, if you have a planet where, interior processes, if you have a planet atmosphere where interior processes playing a dominating role or not, and your atmospheric composition is largely set by the interior atmosphere coupling, this can be also quantified by measuring the atmospheric composition. So thus it is fundamental to know how your atmospheric chemistry is interacting also with your interior processes. Okay. So not only that, it essentially also gives you the idea and also helps you to interpret observations, right? So because we are measuring transmission spectrum from different classes of exoplanet atmospheres, and what I'm showing here on the top right panel for the observations. So this is WAS 39b observations. What you can see here, so beautiful SO2 features. Okay. So these SO2 features, these were the first detection of SO2 in hot Jupiter, typical gas giant planets. So essentially, this SO2 was fundamental for any atmospheric chemistry model, because this SO2 these features cannot be explained without inclusion of photochemistry in the models. And this photochemistry, which I will come back later, is the chemistry which operates in the planet top layer of the atmosphere, and the chemistry is said by the dissociation of the molecules by the incoming photons. And this dissociation is also wavelength dependent. So we see this SO2 in the atmosphere because of these disequilibrium processes. Okay, so we cannot explain this SO2 chemistry, SO2 detections without inclusion of disequilibrium processes such as photochemistry in the atmospheres. And it has also a lot of implications for interpreting the observation using retrievals, because if you just run free retrievals and retrievals with equilibrium chemistry, you will have a hard time to explain these SO2 features. So you need to adopt some technique to handle this photochemistry in your retrieval models. So here, what we are showing here is kind of hybrid equilibrium processes. So your chemistry is both combination of free and equilibrium chemistry. So it is an indirect way of tracing the disequilibrium chemistry in the atmosphere through retrieval. So if you do that, then you get really a good fit, right? So that's why your chemistry, the understanding of the chemistry becomes fundamental even to explain what you are observing today, right? So this is in the context of JWST, but also we are living in an era where next generation, ground-based instruments are coming into the picture, and this ground-based instrument will also help us to characterize different classes of atmospheres. So here, what I'm showing here is HAT 11b. So this is one of the warm Neptune. So as you can see, what I'm showing here, this is basically a model cross correlation analysis. So this is a correlation coefficient with respect to velocity. So what you are doing, your template spectrum, you are shifting with your planet velocity, and you are observing this signal. The correlation coefficient higher represents the presence of the molecules that you see. So for HAT 11b, what you can see, the future ELT, extremely large telescopes like Andes, will be able to understand, will be able to detect this is like ammonia, H2S in the atmosphere, by observing the 1 micron, 1.5, and 1.6 micron band. So these are the theoretical predictions, but at the same time, as I have mentioned, there were degeneracy if you really wanted to use chemistry as a tool to understand planet formations. So carbon, and this is what one of the points that Bart has introduced to us, like only carbon to oxygen ratio is not sufficient. You need to get understanding about other elemental reservoirs. So essentially, what does that mean? It means you need to have good constraint in terms of your nitrogen abundances, sulfur abundances, so that multiple elemental abundances gives you the idea about planet atmospheres. And then this atmospheric composition could be used to infer information about the formations. So combinations of ground and space-based facility, of course, will give us access to the larger inventories, larger set of molecules in the planetary atmospheres. But then the question lies, what chemistry essentially can cause the formations and of these molecules, and how the abundances of these different types of molecules changes across different classes of plants. Okay. And this is largely can be explained by different shoots of chemical processes that happen in the planetary atmospheres. So before I drill into the all the technical details regarding chemistry that is happening in the planetary atmospheres, let us try to understand some of the terms that I will introduce time to time, and let me define this term, because through my experiences, what I have noticed every time we introduce this term, we get confused what we are talking about. So whenever I talk about clouds, by clouds, I mean a visible mass of liquid or solid particles that is suspended in the atmosphere and which is formed through the condensation of atmospheric gases. So this is my definition of cloud in the atmosphere that I'll be covering, okay? When I talk about dust, so these dust particles are basically solid particles that are suspended in the atmosphere, but they did not originate in the atmosphere. So whenever I talk about dust, so that means we're talking about solid particles. They are suspended in the atmosphere, but they don't have the atmospheric origin, okay? Then I will also, time to time, tell you about haze. So the haze are the particles which are formed through the chemistry in the atmosphere, and that results in the formation of involatile solids. So essentially, you are forming, solid particles which has low melting point, okay? So this is your haze particles. Then I will also talk about equilibrium processes. So these equilibrium processes, you can think about, can be defined as chemical compositions, where chemical composition in the atmosphere is solely defined by the local temperature and pressure, along with the elemental abundances that planet has inherited from the early stages. And all reactions are balanced. There is no change over time. So essentially, it means you have reactions where forward reaction rate and backward reaction and reverse reaction rates, they are equal. We also will discuss disequilibrium processes. So in planet atmospheres that we'll be covering, there are two fundamental disequilibrium processes that is happening. One is photochemistry. As I have already mentioned, the direct evidence of photochemistry in the era of JWST was found through the detection of SO2 in Was39b. And also there is transport-induced quenching. Okay. So the photochemistry is photodissociation of atoms and molecules by incoming UV photons, and transport-induced quenching can be, you can think about this is the process that drives your, atmosphere from equilibrium through processes such as convection or large-scale eddy diffusion. So these eddy diffusions can be caused from many processes, such as, if you have planets, which is a dynamical atmosphere, you can think about, circulation of winds can also change the, planet atmospheres. And these processes play a big role in setting up what type of chemistry you will observe in planet atmospheres. There are some of the other processes also, such as thermal inversion. Okay, so thermal inversion of the atmospheres can be defined as like, when you are, going to the top of the atmosphere, suddenly there is an increase of temperature. Okay, that similarly what you see for planet Earth in the, in stratosphere. And for Earth, it is largely caused by ozone, okay, because ozone, can really absorb strong UV visible, photons. And that's why you see thermal inversion for, atmospheres for Earth. For exoplanet atmosphere, we also see thermal inversions in planet atmospheres, and that is largely because presence of some of the molecules such as TiO and VO. So it is also become fundamental to understand how the chemistry of this type of species, TiO and VIO, operates in the atmospheres of hot exoplanets such as hot Jupiters. So in summary, I'll be talking now in two different aspects. First aspect is the equilibrium processes, which which is basically operating in planet atmosphere, when you have your reactions which are not the composition is not changing over time, where reaction rate in the forward reaction and backward reaction is similar. And I'll also talk about the photochemistry, where your planet atmosphere is evolving and your chemistry is largely controlled by incoming stellar photons, and together with you have also thermal chemistry combination, combined with the impact of physical processes such as convection and diffusion processes. Okay, so these three aspects we will go into the detail, and we'll try to understand why in the planet atmospheres equilibrium equilibrium and disequilibrium processes plays a big role in controlling the atmospheric compositions that we measure today. So now I think this is something that Shujan and Jayesh has also covered, but I just for the introduction we should also know how we model these atmospheres. So generally, you have the planetary parameters, which is mostly constant from observations, where the effective temperature of the planets, mass, radius, and other parameters. When you know the planetary parameters for any planet that you are interested in, based on that, you can do, different ways you can calculate what is the expected temperature pressure profile for the planets. One possible way you can think about using parametric models which is constant largely from observations. You can also think about doing full radiative convective equilibrium models, where your radiation process is balanced by your convections, and you get your radiative convective equilibrium pressure temperature profile that can be used for your models to understand the chemistry. And also you can generate your temperature pressure profile with several dynamical processes through general circulation models, GSM models, which are mostly in 3D and computationally more expensive. And then when you have your planetary parameters and your pressure temperature profiles, that's become your initial input parameters for calculations of your abundances for different molecules that you are interested in. Now you can calculate your abundances for different molecules either by considering equilibrium chemistry, where equilibrium processes are considered, or disequilibrium chemistry. When you are thinking about disequilibrium chemistry, one of the prominent way to think is photochemistry is active in this type of systems. When you have both equilibrium chemistry and disequilibrium chemistry in your atmospheres, and you generate your observables. Okay, so this type of observables are potentially, you can think about what is your expected transmission spectrum, emission spectrum, or reflected light spectrum, and whether you see any evidence of equilibrium chemistry and disequilibrium chemistry in the observed spectra that we are measuring today. So by comparing with your models and your observed spectrum, you get the understanding whether your atmosphere is in equilibrium or your atmosphere is in disequilibrium. Okay, and that becomes foundational because that gives you the idea about what type of physical and chemical processes is operating in the planet atmospheres. So now let's first think about how the atmospheric chemistry operates in equilibrium. So let's talk about some foundational thermodynamics. Just think about, you are observing, we are in an era of JWST, and we are observing several hot Jupiters, hot warm gaseous exoplanet atmospheres. And if you think about your gaseous atmosphere, as you go deep in the atmosphere, your temperature is very high. Okay, and as you will see, since your temperature is very high, the chemical reaction become faster. Your atmosphere will be in equilibrium. Okay, and this, whether your atmosphere will be equilibrium or not, that is potentially the parameter that decide whether your atmosphere is far away from equilibrium or in equilibrium, or the reaction can happen or not, is through Gibbs free energy. Okay, and the Gibbs free energy is basically defined as your enthalpy minus temperature and the entropy. Okay, so if you have the understanding about how we can calculate Gibbs free energy, which is a main thermodynamic quantity in the atmosphere, that can give you the idea about whether your planet atmosphere is in equilibrium or far away from equilibrium. Okay. So let's think about, you are thinking about an atmosphere where your reaction is happening and you are, in a mix of gases, and you have a constant P and T. So the second law of thermodynamics tells us that total entropy of an isotopic system can never decrease over time. So that essentially means delta S total should be greater than or equals to 0. And now if you write your total entropy as your system entropy plus the entropy for the surroundings, which is essentially the mixture of your gases. So the chemical reaction that you are interested in and the total entropy for the mixture is basically your total entropy of the entire system, right? So when you know your total entropy, so then the variation of the enthalpy of the system is basically represented by, the variation of the enthalpy of the system is basically, linked to the heat exchange during the reaction. So what essentially it means is your total, heat will be equal to the change in enthalpy of the change in enthalpy of the system. So QP is equal to the delta H system. And now when you have your reactions, so now if your reaction is exothermic, then essentially what it means is some energy is released. Okay, as soon as some energy is released to the system, the your external, the surrounding entropy of the surrounding will be increasing. So one thing is decreasing and one thing is increasing. In order to represent that, there is a negative term. So the total total entropy of the external system then will be the change of the heat divided by the temperature, which corresponds to the enthalpy divided by the temperature. Okay, so now when you have this delta S external, and if you now put this value into your total entropy, then the system entropy minus the enthalpy divided by your temperature is greater than or equals to 0. So now if you just do the rearrangement, then what you will get is your delta H minus T delta system is less than or equals to 0. Essentially, delta G system is less than or equals to 0. So what does that mean is when you are considering a reaction which is in a system with all other reactions simultaneously happening, and if you find the total gives energy of the system, and if your total gives energy of the system is decreasing, that means your reaction can occur. And if your delta G equals to 0, that essentially tells you you are in equilibrium. There is no net change in forward and reaction rate. If delta G less than or equals to 0, so that means your system is going to lower energy state, and that reaction can proceed spontaneously. But if your delta G greater than or equals to 0, then essentially means reaction is not possible. So by minimizing your delta G, you will get the understanding about whether your system is in equilibrium or not. Okay, so that's why calculations of Gibbs energy and the minimization of the total Gibbs energy of the entire system is the most fundamental parameters that decide whether your system, where the reactions, which is largely driven by what type of elements are present at different layer of the atmosphere, are in equilibrium or they are in disequilibrium. Okay. So in summary, basically if you have the reactions, let's say A plus B goes to C plus D, and we will Gibbs energy minimization, then essentially will gives you your forward reaction rate, the rate by which A and B goes to C and D, and the reverse reaction rate is same. Okay. Now, after doing some simple thermodynamic and basic algebra, then what you can do is you can just calculate the total, Gibbs energy with respect to temperature, which is essentially the function of the concentration of, let's say this is Xi, this is representative of how much mole of X is present in I. Okay, so this is not the abundance of I species, rather how much X is present in I. Okay, so here, so this is the concentrations, okay, present in I species, which is the X form. together with the chemical potential, which is GIT by RT. Then there is a pressure term, and then this Xi, and this is the total number of species that is present. So when you have this total, gives free energy, and if you write your chemical potential term again through basic thermodynamics, then what you can do is you can write it with respect to enthalpy of the system. So Gi minus H at 298 Kelvin, and also change of the total enthalpy. So we are lucky because this two term for different molecules, this two term, which is basically the enthalpy and delta Gi 0 minus the enthalpy and the delta H 298, they are available through laboratory databases, such as GenF databases. Okay, so as soon as you have so basically, essentially, what does that mean? You have the constraint on molecules and these parameters, and essentially the entire term GIT by RT through the experimental measurements. Okay. So now, if you really wanted to solve this problem more, computationally friendly way, then what you can also do is you can just fit this, GIT by RT term with your, fundamental constant. And these fundamental constants can then be represented in terms of number of fitted coefficient, A0, A1, A2, A3, A4. And this A0, A1, A2, A3, A4 is basically the coefficient that you can directly get from the databases. Okay. So essentially, you can measure for any system that you are interested in, their chemical potential, the abundances of the species, the coefficient that is needed to calculate your Gibbs free energy. And then by doing the mass balance equations, you also need the total amount of, the species that is present. Okay? When you know this, and if you minimize your, total Gibbs free energy of the system, then you get the idea whether your system is in equilibrium or not. Okay. So that's generally done the same way that I was mentioning to you. So essentially, you have, as I was mentioning, you have the GenF table that is giving you all the thermodynamic parameters. You have your atomic abundances that decides at each layer of your atmosphere what type of elements are present. Now you fit your thermodynamic coefficient based on the GenF table, and you get the initial abundances for the species. When you know the initial abundances of your species, then your primary input for your model is your temperature pressure profile. When you have your temperature pressure profile, you know your thermodynamical parameters, you calculate your total Gibbs free energy of the system, and you minimize this Gibbs free energy using your favorite algorithm. So here, one of the algorithm that we have used in the past is Lagrange method of Stifford descent and lambda correction algorithm. So if you do that, then what you will get for the entire system, starting from your initial abundances.
Hello.
Yes, please.
Yeah, Liton, sorry. Yeah, I think we were cut off from here just now. The audio started. Liton, I had a question in the previous slide.
Yeah.
So the summation is over all the different species, right?
Right. Yeah.
So but in this, the laboratory measurements are done for each species separately. So
right.
There is no. I'm wondering, like, if there is some. We don't expect any catalytic process or something where the presence of some other species affects in any of these way. They're like basically all of them are independent. Like, can they all be independently measured?
Yeah. Yes. That's a very good question. Yeah, exactly. So essentially, let's say, so this could be done, in laboratory because these are not reactions. These are the, thermodynamical parameters for each of the molecules or atoms that you are interested in. Okay. So essentially you are basically, these are the enthalpy, the Gibbs free energy, you have your temperature, you put in your lab, you get the data, what is the heat of formation for this molecule. From there, you can calculate your, the factor, which is basically the Gi minus H29. So for each molecule, separately, at different temperature, we have these parameters, okay? And if you put it in your model, then it goes into your total, system, G system. So it's a sum of all the molecules that you have in your system, right? So essentially, let's say you have 500 different species, and you know the thermodynamic parameters, because we already know the thermodynamic parameters from all these species. You put it, you get your total Gibbs energy. Okay, so they are all independently done and they are not related to one another. Okay, so these are all experiments or sometimes theoretical cases that people do through quantum chemical investigations. You measure the thermodynamical parameters independently for each species. Here you are not doing really a chemistry where, let's say, A plus B going to C plus D. You are measuring the thermodynamic properties individually for each molecules and atoms. Does that answer your question?
Yeah, I'm just trying to understand some. Maybe I missed this something. So how is it that the presence of, like, for example, if I have A and B, presence of A should matter to B for the equilibrium on formation of C and D, right?
Yeah, so that is there in the fitting term, but not when you are getting the individual term which is coming from the thermodynamical data.
Okay, but for the Gibbs free energy calculation, it is not needed.
Yeah, so essentially it's a sum of all the terms that you are doing.
Thanks.
Okay. Can I proceed?
Yeah.
Okay, good. Okay, so now you have your the chemistry model where you have your thermodynamical parameters, as Joe was asking, is basically coming from some databases. Here I'm talking about the JNF data. You use this independently for different molecules, and then you calculate your total system, gives the energy of the system, and you minimize it. And then through the minimization, when the minimization is done, you get your abundances for all species at different layers, which is representative of your equilibrium abundances. And that becomes, your equilibrium state of the atmospheres. Okay. So that essentially what it means is you're starting from your initial elemental abundances, which you choose your elemental abundances, you put your favorite pressure temperature profile. Then in the equilibrium, you get the idea about how different molecular abundances is changing by assuming or by reaching to the equilibrium. So these are all equilibrium abundances for each of the molecules. Okay. But ideally, these atmospheres are not in equilibrium. Okay. But you can get the idea about how the equilibrium composition of these atmospheres are changing with respect to height at each layer, what is the expected abundances. So for that, you need to have the pressure temperature profile, initial abundances, and corresponding thermodynamical data that I was mentioning. Same thing, so this is for Jupiter, the same thing you can do for other hot gas giant planets, right? For example, if you do for Kepler 7b, you pick up your favorite PT profile, you run your equilibrium chemistry, you get the idea about what is the equilibrium abundances for major volatiles that sets your composition for carbon-bearing species, oxygen-bearing species, and sulfur-bearing species, and how at each of the layer your abundances are changing. Okay. So similarly, I would like to highlight here, for example, WAS39b, as I was mentioning to you. If you see here in the atmosphere, what we are showing here, so the abundances for water, CO2, CO, how they are sensitive to your carbon to oxygen ratio. So here, high carbon to oxygen ratio is used. So as you can see, for high carbon to oxygen ratio for WAS39b, you see a lot of CO, but along with you started to see a methane. Okay. And because your carbon chemistry is largely chemistry is largely dominated by methane, presence of the methane, and at the same time you also have other oxygen and sulfur bearing species, but here you don't see the presence of SO2. Okay, because your thermodynamic properties of SO2 is not sufficient to give you enough abundance for WAS39b in the equilibrium. So you need to infer the abundances for molecules which are largely driven by, photochemistry, by invoking how their abundances are changed using stellar flux and how that changes the chemistry. Okay. So if you just summarize that, then essentially what you are observing, in a planetary atmosphere from top to surface. So in the top of the atmosphere, you have very low pressure, you have high pressure here. And in the top of the atmosphere, you see escape processes. Of course, these, some of the results that I was showing you does not include any photochemistry, neither it includes any mixing or circulation processes, but they have chemical equilibrium. Okay. So in the atmospheres where your temperature essentially is very high and pressure in the atmosphere where temperature is very high, we expect to have the chemical equilibrium because chemistry is very fast. As a result, your forward reaction rate and backward reaction rate become equal. And you probe chemical equilibrium processes very close to the surface where you can think about your high pressure regime. Okay. But as you go in the top of the atmosphere, your dynamical processes and disequilibrium processes started to play a big role. So if you observe a planet atmosphere today, and if all the processes that is I'm showing here from photochemistry to mixing and circulations are active in the atmosphere, chemical equilibrium processes is not sufficient to explain what you see in terms of the observed features in the atmosphere. And that's exactly the case when SO2 was observed in verse 39b. So to do this, you need to have photochemistry model. And what you do in the photochemistry model, you solve your continuity equation, which is essentially the conservation of the mass, your number density with respect to time, and this is essentially your flux term, okay? And this is your production term, this is your loss term. But most of the photochemistry model are solved in 1D, okay? Because there are various reasons. First, photochemistry model generally have chemical networks, and you need to solve a number of chemical reactions and essentially a number of differential equations simultaneously, which become extremely difficult computationally as soon as you want to go and solve chemical kinetics in 2D on 3 dimension. Okay, so that's why most of the photochemistry model is solved in 1 dimension. So essentially, this term becomes your del phi by del z. So your number density with respect to time becomes production term minus loss term minus del phi by del z term, which is essentially phi will be the vertical flux of the species. So essentially, how your mixing is playing a role is defined by this term is phi. Okay, but if you just do some simple diffusion calculations, then this phi term, which is basically the vertical flux of species I, comes, which is basically depends on molecular diffusion coefficient for each species, then scale height of species, which you are interested in. Then there is a thermal diffusion spectrum, atmospheric temperature, which is largely depend on your pressure temperature profile, the eddy diffusion coefficient, and also atmospheric scale height, right? So all the physical processes that comes into the picture for atmosphere is integrated within the continuity equations through your diffusion term, okay, through your flux term, how your material get, mixed to the atmosphere, how they are coming from, how they are changing because of the, mixing processes, okay. So essentially, if you really do this, then essentially you can do with the photochemical model. So these photochemical models are essentially what you have as like, equilibrium chemistry model. You need planetary inputs, PT profile. But here, since you like to see the impact of, photochemistry, you also need to impact of stellar flux, right? So you need stellar flux as an additional parameter because that will gives you the idea about how your photochemistry is operating. Then you need eddy distribution profile, which is basically will tell you how your material will be mixed in the atmosphere. then the initial composition for your atmosphere. This initial composition can be based on your understanding of the atmosphere. Either you can start with your atmosphere in equilibrium, and disequilibrium processes such as convections or mixing or the photochemistry started operating and started taking your atmosphere away from equilibrium to disequilibrium. So this sets your initial stage for your photochemistry model. Okay. Now, when you have your initial stage, initial idea, okay, what is my expected PT profile for the atmosphere? What is my initial composition for the atmosphere, which can be largely driven by equilibrium processes? Now you need to solve your chemical kinetics. Now, in order to solve your chemical kinetics, you need to have idea about what type of chemistry is operating at different layer of the atmospheres. In order to do that, in the community, we adopt different chemical networks. So these chemical networks are essentially, large set of chemical processes that is included in one place. And these are largely can be summarized into 4 different processes. One are photolysis process, unimolecular reactions, biomolecular reactions, and molecular reactions. Okay. So if you think about photolysis reaction, which is essentially your photochemistry. So if you have a molecule AB, and if an incoming photons comes and dissociate these molecules, you can have this molecule dissociated into smaller fragments such as A and B. You can have some of the unimolecular reactions. For example, you have a molecule AB can dissociate into A plus B. You can have bimolecular reactions where you can have neutral processes. Just think about hydrogen and OH reacts together, it gives you H2O. Okay. So you can have bimolecular processes, which are very common, and that control large part of the thermal chemistry for the atmospheres, where we are probing with many JWST observations. Then you can also have 3-body reactions, which are basically thermomolecular reactions. So you have A plus B with M can give you AB plus M. So essentially, and the corresponding rate constants are reaction rate coefficients are shown here. So these thermomolecular reactions are where M stands for any third body in the atmosphere. Okay. Most challenging part for doing any chemical kinetics for the atmosphere is not photochemistry, neither unimolecular or biomolecular reaction, but these 3-body reactions. Because these 3-body reactions are very difficult to measure and very difficult to calculate in terms of the rate constants. But they are also potentially physical chemical processes that happens in this region, and you need to know their accurate rate constants and rate coefficients. So when you have all these processes, that you can integrate in your photochemistry model along with your photochemistry, along with your stellar flux and initial composition, which is set by your set by your equilibrium chemistry, can decide what is the global atmospheric compositions. Okay, so initial composition set by your equilibrium chemistry, then your PT profile sets what type of chemistry at each layer will be operating. Stellar flux decides what type of how well your photochemistry will play a role in the top layer of the atmosphere. AD diffusion profile will be deciding how well your material will be mixed and how that will play a role in terms of compositions. When you have all these processes included, then you get the idea about how the composition is changing with respect to pressure and pressure and temperature. So what I am showing here for typical gas giant exoplanets, here I am showing your pressures. Obviously, this is your low pressure region. This is your high pressure region. In high pressure, high T region, as I have mentioned, your chemistry is very high, chemistry is very fast. Okay, and system is in equilibrium. In the top layer, you have your photochemistry dominating. So if you want to distinguish the 3 layers, then ideally through chemical timescale and dynamical timescale, you can distinguish each layer and their corresponding chemistry. So by chemical timescale, I mean how fast 2 atoms and molecules, they will come, react, and they will form some other molecule which will change the composition. Okay, and dynamical time scale is largely set by your mixing processes. Okay, so close to the close to the surface, you have your chemical time scale because chemistry is running very fast. So chemical time scale is much smaller, and dynamical time scale is much higher. Okay. Then you have a region where your chemical timescape and dynamical timescapes are equal. So essentially, we define this as a quenching point. Okay. Then there is a region where your chemical timescale chemistry becomes slower, and dynamical timescale wins. Okay. So these are the region where you see the effect of photochemistry, thermal chemistry. So ideally, whenever you observe any environment, any planetary atmosphere, this transitions from one layer to another is happening in the planetary atmosphere. On the right side, what I'm showing here, dotted line and the solid line. Okay, so just pick up molecules such as C2H2. So this is one of the hydrocarbon species. Okay, as you can see, most of the molecules, so the solid line representative of, you have a disequilibrium chemistry operating in the atmosphere. The dotted lines representative, we have equilibrium chemistry that is operating in the atmosphere. Close to the surface, since you have high temperature, as you can see, and you have started with your equilibrium compositions, you can see clearly your system is in equilibrium. But then you see a transitions from your equilibrium to disequilibrium. So that is just above your quenching point. And then your chemistry started to deviate and start to operate in the top of the atmosphere. And you can see there is then suddenly a change in the top layer for C2H2. Okay, and that's because in the top layer from region 10 to minus 4 to 10 to minus 8, this is the region, or much close from 10 to minus 6 to 10 to minus 8, your photochemistry started to drive your disequilibrium processes. So just for the same atmosphere, if you look at the equilibrium composition and equilibrium atmospheric chemical profile, you can clearly see most of your molecules clearly deviates from equilibrium to disequilibrium. And that's why it is fundamental to understand disequilibrium process in the atmospheres, because most of the planets that we are observing today, we see clear evidence of disequilibrium processes. And disequilibrium drives not only the chemistry that is happening globally, but most fundamentally, disequilibrium chemistry is controlling your atmospheric composition, the top layer of the atmosphere, which is essentially the layer that we are probing through transmission spectroscopy. So if you don't have the clear understanding of how disequilibrium chemistry is operating in the planetary atmospheres, the measurements, the compositions that you are doing today may not give you the full perspective about what physics is happening, right? So that's why it is fundamental to have the clear understanding for same planetary atmosphere, how equilibrium chemistry is playing a role, and how equilibrium, when and under what conditions your planetary atmospheres going away from equilibrium to disequilibrium, so that we know which layer of the atmosphere we are probing and what physical processes and chemical processes we are constraining. So for many of the atmospheric models, and mostly the atmospheric chemistry models, the primary primary motivation is to really understand how the transition from these three layers happens in terms of chemistry, chemical timescale to the dynamical timescale, and how that chemical timescale to dynamical timescale shift changes global atmospheric composition for these atmospheres. And just to come back to the same thing, because as I was mentioning to you, so this is from WAS39b, as you can see the SO2. This SO2, you can explain the inclusion of disequilibrium processes such as what I was mentioning, photochemistry. And this is beautiful results from Shami from the ERS program. So what I am showing here, so this is the SO2 features that I was showing in the retrieval. But of course, in the retrieval, the photochemistry, you are not including implicitly the photochemistry. You are trying to understand impact of the photochemistry through indirect processes, which is such as hybrid equilibrium process that I mentioned. Like by considering you have your atmospheric chemistry, which is neither in equilibrium nor in free, it's a combination of both. With that, you are some kind of making your chemistry much more flexible, so that you get the good fit for your SO2 features. But that's not telling you anything about what chemistry is operating. So retrieval is what you see in the data, but that does not tell you anything about what chemistry is operating. So for that, you really need to go into the models and see what type of chemistry is possible and explaining each of these features. So one such effort was, which is basically change the understanding, and I would say change the field so much, and made all of us to think, why, disequilibrium processes such as photochemistry plays a very strong role in controlling the atmospheric compositions for, atmospheres. Okay. So here, what I'm showing here, what is the possible way you can make SO2, okay, in the atmosphere of WAS 39b. Just forget about this data set. Just see, they have, in this paper, Shyama has tried to run 3 different models with one of his photochemical model, Vulcan, that today Priyanka will also demonstrate how you can use this open source code. So with Vulcan, if you are playing with your, metal city, okay, 5 times solar to 20 solar, then you can see clearly how your, fit to your transmission spectrum is changing. Okay. But if you look at your the base model, which explain your SO2 features, which is essentially where you need 10 times the solar abundances, the chemistry that you see here is, in order to form, SO2, you need to have, OH, and this OH can oxidize your sulfur to get your SO2. So this OH is only available in the top of the atmosphere. You can get it if you dissociate your H2O through H nu, and this H nu can dissociate water, which is basically direct photodissociation of water, and it can give you OH plus H. Then this, OH can react with your, S, can give you SO, and this SO can again react with your OH because you have already ample amount of OH, and can give you the SO2. So this is one of the channels, but there is also another competing channel where you can also dissociate H2S and get the atomic sulfur. Okay. So the combinations of, there is also currently in the community discussion about how the, the photodissociation of H2S plays a role in the atmosphere. So the combinations of the photodissociation of water and H2S, and through successive channel of the thermochemistry, can lead to the formation of SO2. And without having this impact of the H nu, which leads to these fragments OH and atomic sulfur, we will not able to explain the observed chemistry or observed features of SO2. Okay. So that is one of the key findings from JWST ERS program. But this is, yeah, please.
Can you please go back to the last slide?
Yeah.
I had a question. So in this graph, wavelength versus the transit depth, there are more signatures which probably are not very prominent, but they haven't been identified. So is it because those molecules have not been added, or what's the consensus on that? So SO2 seems to be identified, but there are some which are close to 4.5 and 5 micron. What is your take on that?
Yeah, so if you see from, this is 3 to 5 micron, right? So if you look at these features from, here, for example, 3 to 5 micron, as you can see here, there is a SO2 feature, there is possibly H2S. Retrieval is speaking of H2O and CO2. So in the retrieval, you see all these features, right? So which is primarily your water, CO2, SO2, and probably some fraction of H2S. But if you go to the forward model here, they're really not trying to fit this bump, okay? Because they are more interested to, consider the CO2 together with SO2 and some combination of H2O, okay? But not trying to individually feed each of these minor bumps that you see here. So this is a forward modeling fit. So that's why they are not showing all the features. But the key take-home message is the most strongest features that you see here is the SO2 features and the CO2 features. And that's what exactly you see, because if you look at the retrieval from 2 to 5 micron, you have combination of H2O, CO2, H2S and SO2 and CO2. So they are beautifully fitting these H2S feature, SO2 features and CO2, but not necessarily talking about the possible presence of H2S, because which is very less, of course. But this SO2 could be fitted in the forward model, but with the inclusion of detailed photochemistry. So that's the key point.
Right. Okay. Thanks.
Okay, so that is about how equilibrium chemistry and disequilibrium chemistry shifts to
Sorry, on that question. So you mentioned that while doing forward model, you don't have to include all the. You can specifically focus on the valence region, right? But that we can do only if we know for a fact that nothing else will be contributing in these wavelengths that we are fitting. So is that so done sort of like in a step-by-step process that first you identify all possible molecules that we should worry about in a certain wavelength. For example, in this case, we know from some other analysis that the H2S cannot be affecting the signal 4 and 4.5 micron where SO2 CO2 is, so that we don't have to include them in the forward model. Is that how that is done?
Yeah, so here I think what the year is, okay, so as you can see, this is almost 3 years old paper. So I think the initially the way the ERS team has done, which is basically if you are using, when you have the real data, okay, so basically if you see the first paper of ERS, when they have tried to fit CO2, they all have done the forward modeling fit, but not simultaneously consider all other molecules, okay? But I completely agree with you. If you are really, ideally, your forward model should fit all the features simultaneously, as like what you are doing for the retrieval. But that is not here what is done. Here, the entire goal was to fit the most prominent features of SO2 together with CO2 and try to see how well the major features like water is explained. But of course, if you see from I would say 3.2 to roughly 3.7 micron, there are features that you don't explain here in this forward model, okay? But you just trying to explain in detail the chemistry that you see for SO2, okay? So this is, I would say, initially when you have an atmosphere, you use your retrieval to get idea about what type of possible molecules that is present, because you can't do detailed photochemistry in your retrieval. Then when you have the idea about all your possible molecule that is present in the atmosphere, typically, then you do more robust forward model to understand the robust features that you see or identify in the model, okay? So that is what is done here, okay? But not simultaneously trying to fit all the features using forward model. I think this is not yet done also for the entire range, because if you see, ideally, if you have a base forward model, you should have a base forward model that should able to explain all the features that you see from sodium, potassium, water, CO2, SO2, probably some percentage of H2S, CO2, CO, SO2, and water. But that is not yet done because they are mostly interested in the SO2 and CO2 in these features, and that's what they have done in this paper. Okay. Does that answer your question, Joe?
Yes, thanks.
So, in summary, so I would like to, make another point here. So retrievals are very good in terms of to get the idea about what is your, chemical diversity, possible chemical diversity you see in the atmosphere and how confidently you see some of these features. But if you really wanted to probe detailed physics and chemistry, then forward models such as what is shown here on the right side is fundamentally important, because that gives you the idea about what chemistry is operating at each layer of the atmosphere, along with how sensitive they are in terms of the initial abundances for the atmosphere, which is essentially initial composition for the planetary atmosphere, and also what type of stellar flux you need. If you don't have the measurement for such star where you are observing your planet, then you will not have a very good constant in terms of your photochemistry. So it becomes auto model dependent. So forward model is the only way you can really get the understanding of the detailed photochemistry in the atmosphere, understanding of detailed thermal chemistry that is operating, and also how your photochemistry is competing with thermal chemistry like two-body and three-body reaction that is happening below the photochemical layer. Okay, so that is fundamentally important to understand. So, and of course, now if you do this exercise across scales where you have your photochemistry, where you know your equilibrium chemistry, you know your disequilibrium chemistry, and you need to understand how each of these processes, vary on the, physical assumptions. Okay. So what I'm trying to explain here is, so this is a very complicated plot, but, let me take you through with this. As I have said, and if you have followed other two atmosphere talks, it is very clear you can model your atmospheres. Atmospheric modeling is largely sensitive to your pressure temperature profile. What type of pressure temperature profile you consider, and this pressure temperature profile largely come from mostly radiative convective model or your 3D general circulation models. Okay, but they are not very straightforward to do. So that's why, different assumption of PT profile and different model dependent PT profile can also create strong biases in terms of what you see in terms of your, predictions for the atmosphere. So to do this exercise, so what type of thorough assumption that goes into the model, what we have done here. So this is kind of a shoot of all possibilities. This is just to show you an example. What we have looked into in the past. Okay, so you have the planet atmosphere, and the atmosphere is modeled with radiative convective equilibrium. Okay, and then you are solving your chemistry, 1D chemistry, both in equilibrium configuration. So essentially your atmosphere is in equilibrium and also in disequilibrium. And then you are doing again your additive transfer in 1D. In another case, just think about you have your atmosphere model with 3D GCMs, and from the 3D GCM, of course, since your chemistry is not in 3D, chemistry still operates in 1D. You are taking median day side and median terminator side TP profile. You are also getting the idea about the wind velocity. So essentially, that will help you to get the understanding of your diffusion, eddy diffusion. When you have that, how the observed composition, so observed chemical composition that caused by different PT profiles coming from different types of physics models changes your synthetic spectrum. Okay, so let me summarize again. So earlier what we looked into, whether your atmosphere going from disequilibrium to whether your atmosphere is moving from equilibrium or disequilibrium, largely controlled by the PT profiles along with the processes that you have considered. So now we are looking into how the assumption that goes into typical models in terms of getting your PT profiles, whether that also can cause observable differences in terms of your equilibrium composition and disequilibrium composition that you measure today, and whether these differences can also is visible in terms of what you observe in terms of the spectrum. So that then becomes an indirect way of constraining the equilibrium versus disequilibrium processes under varying temperature pressure profile. Okay, because most of these planets that we are measuring, this temperature pressure profile constant is very weak. Okay, so this is largely model dependent or coming from retrieval models. So ideally, one should think about how global PT profile is changes through the dynamical processes. So essentially, you need general circulation models, but that is more complicated because even if you have the 3D GCM models, you can't. We are far away to do 3D chemistry because chemistry in 3D will be extremely challenging with such a big chemical network where you have thousands of reactions operating for different molecules. So to do that, so if you just look into the distributions, so here it's a very busy plot. Let me just take you through this to give you the idea. So here I am on the left side, I'm showing the equilibrium abundances. Here I'm showing the disequilibrium abundances. Okay. So even the equilibrium abundances, Okay. If you just look into the two solid, here the solid lines and the dotted lines, these two comes from two different physical model, one from the 1D RC model and another from the, dayside average PT profile coming from the GCA model. As you can see, even for the equilibrium composition, your model PT profile, even if you have a wrong PT profile, that gives you completely different equilibrium abundance for the same atmospheres. Okay. Same thing here. For the disequilibrium chemistry also, which chemical profile, is it from your 1D RC or your 3D GCM, has a strong abundances, strong shift in the abundance profile throughout the atmosphere. For example, if you pick the molecules which are the major reservoir, for example, if you pick, let's say, CH4, in the top layer, you can see CH4 so strong dependency. Okay. Then if you look at the, abundances for, ammonia, okay, it also shows strong dependency. Okay. So not only the, equilibrium, disequilibrium processes is sensitive to just your PT profile, but what PT profile you are using, which PT profile you are using in the atmosphere, that plays a big role in terms of your atmospheric abundance measurement. So it is fundamentally important to have right temperature pressure profile. And that's why climate modeling is very fundamental in order to get the understanding what is your true atmospheric composition and what processes at each layer of the atmosphere is doing. Okay. So this is about the TP profile. But what about the complex chemistry? Okay. The complex chemistry. So because there are talks about prebiotic chemistry. Do you see any possible evidence for complex chemistry that is happening in the atmospheres? So here what I'm showing, cyanoacetylene in the atmosphere of, typical super Earth. Okay. You can think about this is like a GG1 on 3-2b planet. So what you can see for a typical super Earth, a long chain hydrocarbon species like AC3N, which in long been postulated, can have a prebiotic chemistry. Like even in the atmosphere, we can have, if you have sufficient thermal chemistry and photochemistry in the atmosphere, you can really build high concentration of AC3N, which is one of the complex organic molecule that potentially participate in the prebiotic chemistry that one can think about whether prebiotic chemistry, evidence of prebiotic chemistry is possible in the atmosphere or not, is also seems to be possible through atmospheric chemistry. I'm not going into the details of whether we will be able to observe this molecule, but atmospheric chemistry tells you can have formation of, if you have right chemistry in your system, you can really form such type of complex molecule in your system. And AC3N long been assumed to be one of the key precursors for the formation of large prebiotic molecules. And we can see that how AC3N is showing peak abundances of the order of roughly 10 to the power minus 4 to 10 to the power minus 3 in the top layer from 10 to minus 4 to 10 to minus 6. That's essentially the layer potentially we are probing. So there are potentially different classes of super Earth atmosphere where we can see possibly the chemistry of AC3N, which could be potentially linked with large possibility of large carbon chemistry and formation of more larger complex carbon chemistry that is happening in this type of atmospheres. So this is for super Earths. I mentioned for hot Jupiters how equilibrium and disequilibrium chemistry operates and how we see differences and how they produce observable signatures here for the super Earth. But what about Earth-like planets? Okay, so this is a typical Earth-like planet atmospheres. The PT profile I'm showing. If you use such PT profile, so you can see typically, for a typical Earth-like atmosphere, how different chemical abundances varies. Okay, why it is becoming strongly important, important to understand how photochemistry plays a role in Earth-like atmospheres, because many of the molecules that you would like to detect in Earth-like planets as a potential biosignatures gases, you would like to understand if that particular molecule can be produced with local atmospheric chemistry before getting any idea whether some fraction of the composition that you are measuring is coming from the surface atmosphere interactions or any biological processes. So if you really want to understand chemistry of Earth-like planets, here atmospheric chemistry plays a much bigger role, because then you need to get the full understanding whether atmospheric chemistry for potentially all the biological biosignature molecule that you are interested in, if they have an atmospheric chemistry origin, then they would not be treated as a potential biosignature. So it is important to also look into the details of how atmospheric chemistry plays a role in Earth-like atmospheres. Okay. So I will not go into the detail, but just to tell you, if you have typical Earth-like atmospheres, and if you, as you can see, many of the features, we will be able to see in the in some of the closest Earth-like planets, such as ozone, water, CO2. So it becomes more fundamentally important to ask this question whether all the features that we see, how much is contributed from local atmospheric chemistry, or is there any potential biological source, or is there potentially an interior process that can essentially explain the observed features? So that is true also for the thermal emissions, okay, for other species such as O3, N2O, okay. So then in that case, you can use atmospheric chemistry as a tool to understand also detectability of different biosignature gases and use it as a key criteria to determining your goal of detectability. For example, if you really would like to understand, for example, you can consider different types of models, and you start with different Earth-like compositions, and with a different Earth-like composition, you try to vary your surface compositions and also the deposition of molecules in the boundary. So by playing with the boundary conditions with your atmosphere and playing with the abundances for different molecules, okay, you can get the idea which molecules, how much you need as a contribution from the interior to the atmosphere in order to see them in observable amounts. So in that case, your atmospheric chemistry becomes indirect way, though you are not modeling any biological process nor any geological process, but your atmospheric chemistry becomes an indirect way to talk about interaction between atmosphere and interior processes. So that's basically your equilibrium chemistry that happens, equilibrium chemistry to disequilibrium chemistry that happens from very hot gas giant planets to Earth-like planets, and how we can use them as a tool not only to understand what physical processes is operating at different layer of the atmospheres, but at the same time, we can use them as a tool to better understand ask the better questions, such as the molecule that you are observing, whether really they are true biosignatures, or is there any contributions from abiotic pathways. So that's why atmospheric chemistry also becomes a key fundamental tool to understand astrobiological aspects of any planetary atmosphere that you want to model. So this is for the atmospheric side, but what about what chemistry is operating on the origin sides, okay, when planets are forming? So many of the molecules that we are observing in the atmospheres, as I have mentioned, they are mostly simple molecules, okay? But when you are observing when these planets are forming in the very early stages, in the disk stage, we are observing much more complex chemistry. And this complex chemistry that we are observing today in early stages, even before planets have started to form, it is largely because you have complex interactions between gas. Yes.
Yeah, Liton, no, just the timer 10-minute is remaining, I just mentioned.
Okay. So I'll just briefly tell you that. So essentially what I'm pointing out is, in planetary atmospheres, we are observing key chemical species, atoms, and molecules, which are largely a main reservoir for carbon and oxygen. But we are really not in yet there to discover complex molecules in the atmospheres. Okay, so you can think about the most complex species we have discovered so far in the planetary atmosphere, in exoplanetary atmosphere, is SO2. But in the regions where these planets are forming, so essentially in the disk and young stars, and also in photostellar region, we are observing many more complex molecules. Okay, so here on the right, on the left side, what I am showing some of the key gases key ions that we are observing in photoplanetary disk, like N2H plus, DCO plus. If you like to hear more, attend the poster of Parash, you will see that how this type of molecule essentially plays a role in setting up initial composition for future planet atmospheres. But at the same time, you can also see the hot gas emission from many disks around young stars using JWST observation, and they are showing very complex emissions from complex hydrocarbons like such as C6H6, C4H2. And this complex hydrocarbon chemistry is only possible if you have very high carbon rich atmosphere. So basically, essentially, if you have high carbon to oxygen ratio. Many of the atmosphere that we are observing today is also very carbon rich. We are observing very high carbon to oxygen ratio atmosphere. At the same time, because these regions are combined with gas and dust, and they have a strong gradient of temperature. So not only we are observing the gas, but we are also observing the features from the dust in form of ices. So the dust in form of ices, we are observing many complex, organic molecules like formic acid, methane, methanol. Now the question lies, how we are making this complex species, in the atmosphere, in the regions where these planets are forming. Because earlier I talked about how equilibrium chemistry and disequilibrium chemistry playing a key role in setting up the atmospheric composition of the planets. But now here, there are many more complex organic molecules we are observing, which we don't see in the atmosphere. So what chemistry is operating in the earlier stage that dictates the detections for such molecules? So I will not go into the detail, but due to lack of time, but what I can tell you, the answer lies in the interaction between gas phase and grain surface processes. Okay, because as I mentioned, when we are observing atmospheric chemistry through the detections for multiple molecules, we are measuring the bulk carbon to oxygen ratio through detection of species like CO2, CO, SO2. We are mostly probing the gas. But when we are observing the regions where these planets are forming, we are probing both gas and dust. And since you have a strong, gradient in the temperature, there is a complex dust chemistry that is happening. Okay. Here, what I am showing, you have a surface of tiny dust grains, which will essentially grow in the future and form bigger planets. So this is basically, you can think about, this is the precursor for future planetary core. When you are in a photoplanetary disk stage, this core is hosting very complicated ice chemistry. Because you have a dust, your temperature is very low. It can go from as low as 10 Kelvin. So dusts are covered with ices, and when ices are present on the dust surface, there are complicated chemistry happening, such as if your dust is exposed to UV radiations, molecules that is present on the dust surfaces of the ice grains, they can dissolve. But if you have a molecules which have very strong binding energy, they can also stick to the grain and stick to the core of the mantle as it is, which cannot be dissociated by incoming photons. Then you can have multiple layers of ices, okay? And each layer of ices can interact with each other. And on the surface of the ice phase, your atoms can diffuse, they can react, And the diffusion can go from different way. Atom can directly react with another atom, or they can diffuse, meet another reactant partner, and then react, and then they can form another molecule, and they can get dissolved in the gas phase that we are observing. So all these processes comes into the picture when you are forming a planets. Okay, so the chemistry that is happening during the formation is much complex than chemistry that is operating in the atmosphere, largely because during formation, your chemistry is happening both in the gas phase and also in the dust surface, and the gas and dust is continuously interacting through processes such as absorption, diffusion, and desorptions. Okay, so just to give you an perspective, same as like in planetary atmosphere, here also you can have two body reactions, you can have three body reactions, you can have photodissociation reaction, which is also similar like a photochemistry that you were handling. And each of these processes not only happening in the gas phase, but they're also happening on the surface. And they're continuously interacting with each other and setting this, controlling the abundances for formation of future species. So I will escape this part and go here. Sorry, yeah. And so essentially, so if you know in a region where you have your formation of future planets, complex gas phase and dust surface chemistry is happening, and this dust and complex gas surface chemistry can give you different abundances at different locations of the disks. Okay, because each of this location is controlled by ice lines for different species, as I have mentioned before. So essentially, if you are looking at the interior of water and CO2 snow line, you will end up having different CO2, different carbon to oxygen ratio. If you're looking at the exterior for your snow line, you have different carbon to oxygen ratio. So if you now think the complex gas and ice chemistry is happening in this type of system, and they set the initial inventory for your initial carbon, oxygen, nitrogen inventory, from where your future planet is accreting the gases. Okay, so this is the abundances in the gas phase, carbon abundance, oxygen abundance with respect to hydrogen, and this is the typical carbon to oxygen ratio at different location in the disk. And here, what I'm showing here, so two different possibilities. One is the system is having a low ionizations, another is high ionizations. Okay, so if you plug in all this initial composition that is set by your complex chemistry that has happened in the photoplanetary disk stage, and if you use them as a key tracers and in your future planetary atmosphere model, okay, this is what you see. Okay, so here what I'm showing here, so just one profile I'm showing, if you are looking into the initial abundances, which is basically you are assuming your planets has accreted the gas at 1 AU, which is a low ionizing environment. Okay, then what you see here, each of your equilibrium, each of your disequilibrium abundance profile, how they are changing. So there are two cases, the dotted lines for the non-inverted PP, basically non-inverted TP profile, and this is inverted. So that's not important here. But what I'm pointing out, your atmospheric chemistry and atmospheric abundances are largely sensitive with what is the initial composition of your atmosphere that you have started with, and how they were set by the local physical and chemical processes that happen in the photoplanetary disk. And if you use this as a tool, then atmospheric chemistry become a key foundational knowledge for you to understand how your atmosphere can be used, how your atmospheric chemistry can be used to infer where and how these planets might have formed. So one such example, but this is of course by considering the simplest assumption, which is basically typically your planet has this will work only in the core accretion scenario. Okay, so just think about, if you have a hot Jupiter, if you ask the question, if your spectrum is dominated by water, if it is yes, does the water has CO2 signatures? if it has CO2 signatures, then it might tell you that planet might have formed in a low ionizing environment with carbon to oxygen ratio of 0.53, where most of your gas in the disk is inherited from early stages of planet formation. So essentially, you have even probing even before the disk was formed. So essentially, pre-stellar stages. But if you have water, but if you don't have CO2, okay, because now your atmospheric chemistry will show CO2 abundances should be much lower, then essentially you are probing low ionizing environment with lower carbon to oxygen ratio. And still you are probing with inheritance. Same thing if you have water dominated spectrum, but if you don't have, ACN, okay, then what kind of possibility you end up with? So by looking at your atmospheric abundances, which is largely set by your initial composition for your atmosphere, either you take this initial composition for your atmosphere driven by your fundamental disk physical and chemical processes, you can get some idea about what is the environment where this planet has formed. But of course, it comes with the challenge because most of these planets that we see today, the processes such as migration plays a big role. And then we wanted to see how the migrations can also change the carbon to oxygen ratio and other physical processes that is happening in the disk, and that has any impact on these predictions. So this technique would reasonably works well if you're assuming you are in a core acquisition regime. Okay. So essentially, to summarize, the atmospheric chemistry is key for many of these instruments that returning a lot of data, such as James Webb. Okay, and atmospheric chemistry is playing a big role understanding what this atmospheric composition is telling us about local atmospheric physical and chemical processes, along with how they potentially link with the formation. And in the future, instruments such as Habitable Observatory, LIFE, and some of the potential Indian concepts such as XWorld might help in this regard to constrain more atmospheric chemistry in the planetary atmosphere. With this, I will end here, and I'm happy to take any questions that audience might have.
Hello, I'm audible, sir?
Yeah.
One of your slide, you mentioned that 3D GCM, the TP profile that's coming from 3D GCM and 1D RC, if you use photochemical model for 3D GCM, that might shift the elemental abundances from 1D RC, right? So in that case, which model should we rely if we want to do retrievals or if we want to do transmission spectrum, transmission spectrograph? In that case, which model should we rely? Should we rely on 1D RC or?
Okay. So I would say 1D RC is a very good way to go, but for 1D RC you will not have a constant on the AD diffusion. So essentially your KZZ parameters. So that you can get from the GCM, and as you know, how sensitive is KZZ in controlling your chemistry. So 1D RC is a good to go because GCM is because you need to run grids of model to fit your spectrum. Essentially, one GCM model will not work, and then it has become computationally challenging also. Okay. So I would still consider 1D RCE along with good handle on the atmospheric chemistry, which is essentially means you have a disequilibrium chemistry models, can give you the good understanding of your observed spectrum. Okay.
Okay. And just one more question. You also mentioned that to run, in the photochemical models, there are two processes that dominates. That's photo dissociation and the vertical mixing, which also includes convection, right? So when we are talking about convection, is it like when we are putting the temperature pressure profile inside the photochemical model to run, that's where we are considering the convection, or is it like the photochemical model should have some sort of independent component as in to do the convection part?
So the convection is coming through indirect way, which when you are using your 1D RCTP. Okay, because your mixing is largely controlling your chemistry here. So you are not putting the convection directly, it's through your PT profile.
Okay. Thank you.
Yeah.